So I'm giving this another try. I think I maybe have it figured out a little bit better, so we'll see how it goes. I'd like to finish Chapter 3 in this recorded lecture, and I'll send an email attachment with some suggested problems for you to work on, and we could talk about those in class when we meet on Tuesday, the 16th. Did I have that right? That's right, Tuesday the 16th. All right, so at the end of Chapter 3, we're now doing some chemistry. As I write here in this section, we're applying the first law of thermodynamics to energy changes in chemical reactions. All reactions, and what's a reaction? When you make and break chemical bonds, involves changes in energy. Of course, physical processes also involve changes in energy, like solvation, dissolving things in a solvent. Phase changes do also involve energy. Open air reactions, or other constant pressure reactions, often have a focus on the heat transfer. And the reason is even if a reaction is producing gas and perhaps doing some work, usually that's a small fraction to the amount of energy that's released in the form of heat. There are exceptions, but the vast majority of reaction that you've done in chemistry labs or will do involve transfers of energy in the form of heat. So once we say we're doing a constant pressure reaction, then that means that we are dealing with changes in enthalpy. So consider this easy reaction. So it's the combustion of 1 mole of graphite with oxygen at a pressure of 1 bar. Now the assumption is that you have excess oxygen here, and the product molecule is CO2 gas. If the reaction is done under these conditions, it's said to happen in a standard state. That's what the little naught means. Now, it's not true that the temperature is defined as the standard state. Now, you might have learned in a previous time that there is something called STP, standard temperature and pressure, but that's not what this is. This is considered to be a standard state reaction. So the any element is in its standard state. In the standard form of carbon is graphite. The standard form of oxygen is O2 molecules. Any gases are at 1 bar of pressure. Now, 1 bar of pressure is 100,000 pascals. 1 atmosphere is 101,325 pascals. But we often tabulate data at 298, which is why you've seen it so often. So if this reaction is run under standard conditions, the delta H is minus 393.5 kilojoules per mole. So the combustion of the graphite, of course, gets very hot. You might be wondering, well, what do you mean you're running a reaction at 298? Of course, you're going to produce heat energy, but you're measuring the heat change under the conditions stated. Any heat that was given off during the cooling process is part of the enthalpy change. So this is how we say that a reaction is occurring at 298 K. The reaction is occurring at that temperature. So in general, the change in enthalpy in a reaction is going to be equal to the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. Remember, the standard way that we use the delta symbol is to do final minus initial. We're going to see an exception of that later in this lecture, but for now, we take the product enthalpies minus the reactant enthalpies. Now, these values have a name. They're standard molar enthalpies. Now, such values really can't be measured. You can't get a mole of something and do an experiment which measures its sort of internal enthalpy. It just doesn't have a way of being isolated. Only values that are relative to an arbitrary reference. I like the analogy they use here of sea level. So we talk about maybe an elevation of Mount Everest compared to sea level, where sea level is 0 elevation. Chemists have chosen standard heats of formation as the sea level. So when I say a standard enthalpy of formation, that has to do with the delta HF naught of a reaction is the creating 1 mole of a substance from its elements in their standard states. Okay, so I know you've seen that before, but if you can get a table full of heats of formation, or enthalpies of formation, I should say, then you could assemble them to get the delta H of a reaction. Now this data is usually collected at 298K for convenience. So in the earlier example, when I did the combustion of the graphite, if you want to know the delta H of that reaction, you can look up the standard heat of formation, or standard enthalpy of formation of CO2 gas, the product, minus the standard enthalpies of formation of the reactants, in this case, graphite and oxygen. Now by convention, or really I should say by the definition, because we're defining delta H of formation as creating something from its elements, all elements have 0 enthalpies of formation. So that makes this very easy. You only need to look up a single number to get the delta H of that reaction. As I say here, you can get very precise values of delta H of reaction using this technique. Now, sometimes the technique might not be available. For a variety of reasons, you may not have access to a delta H of formation for a particular chemical entity. In that case, you can get a less accurate technique, but yet an okay technique, by assembling bond energies. So in this case, the delta H of a reaction is equal to the sum of the bond energies of all the reactants minus the sum of all the bond energies of all the products. Notice the difference in what comes first and what comes second compared to the reaction above. So in this case, you're breaking all the bonds on the reactant side of the reaction and then subtracting all the strengths of the bonds of the products. So don't get those confused. So when I said you look up those delta H's in a table in the back of your book, where did they come from? Someone somewhere had to do some experiments, and you're right. The direct method can generate, or has generated, data for a few compounds. So here's an example. You've got tetraphosphorus decaoxide. If you have 4 moles of white phosphorus, which is the standard state of phosphorus, and 5 moles of oxygen gas, you get a delta H of that reaction of minus 2984 kilojoules per mole. And that's a reliable number that you could measure in calorimetry in a lab. But many compounds don't react quickly enough for it to be practical, or they might just be too costly. You don't want to spend necessarily thousands of dollars doing a reaction just to get a value of delta H, delta HF. Also, you guys are chemists enough to know when you do a reaction, you may not get a pure product like you think you want to get on paper, or think that you're writing down on paper. Side products are a big problem. So you have to do an indirect method. You apply Hess's law to several non-formation reactions. And so I'm going to do one of the examples from your textbook right now, example 3.9. So for example, we want to know what the delta H is of 2 moles of carbon plus a mole of H2 gas. The states are important here, to form a mole of acetylene. Now, because I'm going to assume the standard state of carbon, I have to write graphite there. No one wants to consume diamonds to make some acetylene. So here's 3 reactions I'm going to write in order to assemble them. This is one way you could use it. You may like a different verb, but manipulate them to get the delta H of the reaction that we're interested in. I want to point out something that is a preference of mine that I don't know, I can't recall asking students if this bothers them or not, but many textbooks more recently, of course I'm ancient, I learned how to write delta H of reaction this way with RXN as the subscript. Many textbooks have been putting the R next to the delta prior to the H. You can't teach an old dog new tricks. So unfortunately, I won't be writing that form. I'm just so used to this, it's my preference. So I have 1 mole of hydrogen gas, a half a mole of oxygen gas going to water liquid. And this one is another negative number, minus 285.8. Something I came across in the reading, they kind of stated that negative values of delta H when you're doing the bond energy method are more reliable. I can't recall reading that before or learning that before, but I'll take Dr. Chang's word for it. So here we have a third reaction that's pretty exothermic. And I see that my White Sox game is about to start soon, so I won't blather on too much here. But we have the technology to change the colors on my pen, so how am I going to assemble these 3 reactions to give the overall reaction on top? Well, it's kind of a bit of a game. You want to look for one of the chemical species at a time and use multipliers or even reversals of reaction to get what you want. So what I mean get what you want, I want to put a big 2 in front of the first reaction because I need 2 moles of graphite on the left. And the first reaction is the only one that contains any graphite. So that seems pretty straightforward. I noticed that my product molecule, acetylene, is on the right side, of course, but my source reaction is on the left, and I've got 2 of them. So I'm going to say I'm going to multiply the third reaction by a negative 1/2. The negative meaning I'm going to flip the reaction and then multiply everything through by a half, including the energy. And then finally, I see that, how do I use the second reaction? Oh, I see. So it looks like I've got a water molecule in the third reaction that's going to end up on the left-hand side with a 1/2 in front of it. So I'm going to have to cancel that. The only way I can is to have a 1/2 of water on the right-hand side. So I'm just going to leave the second reaction as is, but multiply it by a half. Let me summarize what I just did by multiplying all my factors through. And I'm going to be a little lazy and not write all my states just to save some time because I see my power's running out. So 1/2 water. And then finally, I want to flip the reaction, so I want to put 2 CO2s plus 1/2 H2O going over to 1 acetylene, and then 5/2 oxygen. So that's going to turn that to a positive 2598.8 times 1/2. So if I add all of that, I've got a lot of canceling to do. Did I make an error? Yeah, I found my error. If you were following along with the book, I forgot to write a 2 here, and that was the tip-off to me that I had made an error. So, it there looks good, and for that reason, I don't need the 1/2 in front of the second reaction. So I'm going to leave that as is. The 1/4 was the fraction that kind of gave me some heads up that I had made an error. And so now things are going to cancel just right. So let me see what if I could do that quickly here. The water is going to cancel. The 2.5 oxygens cancel. 2 CO2s. So I get 2 carbons plus an H2 going to acetylene, and my calculator is going to hopefully give me the right answer. 2 times 393.5 negative minus 285.8 plus 0.5 times 2598. I get 226.6 kilojoules per mole. I'll leave it to you to do some other examples that I didn't do and put those in the email. You know what? I've got one more slide that I'll go over briefly. Remember when we said that the standard state doesn't have a state temperature, a set temperature? So now is when we're going to deal with reactions that are run at other temperatures. Heat capacities are the key to this. So as we said, delta H's of reaction are really a sum of all the enthalpies on the product side minus the enthalpies on the reactant side. What we're being asked to do is to find out how changing the temperature affects the reactants and the products. So we want to see essentially what this differential is saying is what's the change of these quantities with respect to temperature. Well, on the right-hand side, if you look carefully, this is essentially a definition that happened earlier in the chapter. The rate of change of enthalpy with respect to temperature, by definition, is the heat capacity at constant pressure in this case. So if you could have the sum of the heat capacities of the products minus the sum of the heat capacities of the reactants, that difference in heat capacities will tell you how the delta H of the reaction is going to change. And so essentially that's the derivation that happens here. It generates something called Kirchhoff's law. So it allows you to calculate the change in the delta H of a reaction if you know the difference of the heat capacities at the two temperatures. Okay? Now, this equation assumes that you have a constant value of heat capacity at the different temperatures. So the heat capacity of, let's say, the product at the lower temperature is the same as the heat capacity at the higher temperature. What the delta is referring to here is the delta between the products and the reactants. Let's do an example. So this is example 3.11. Simple reaction, 3 moles of oxygen going to 2 moles of ozone. And the delta H of reaction when you run it at standard conditions, which is 298 K, the pressures are at 1 bar. Calculate the delta H of this reaction if you ran it at 380 K. Well, if you assume that the heat capacities are basically the same for ozone and O2 at either temperature, you could look those up in an appendix, find their difference, and then multiply it times the difference in temperature, which is exactly what I did here. In this example, it's not appreciably different. You end up having a 1 kilojoule, approximately a 1 kilojoule per mole greater delta H value at the higher temperature. So it's negative. So it's 1 kilojoule less at the higher temperature. So a lot of work for not a very big difference, but I did want to illustrate for you that the assumption of everything happening at 298 is usually going to give you a pretty good thumbnail value for the delta H that's associated with a reaction. All right, I'll let you go with this and give you some problems by email. Bye-bye.